Bismillahirrahmanirrahim. Today we will discuss volume and flow measurement. These are some questions made of me for the master degree. I want you to have a look on the figure on the left downwards, where we can see the flow meter, which we'll discuss later on, to find the difference between the bobbin whenever it's in the upper part of this tubing system or in the lower part. You can see that annular space, which is the space around the bobbin, between the bobbin and the tube. It's much increased in the upper part than the one on the lower part. First of all, we are going to discuss what we call gas volume measurement. We are going to discuss almost 6 points. This is the first point. You see, what's the difference between volume and flow? Flow is the matter of volume per time. You see, the problem of flow, of course, it could be a liquid or a gas, is that the gas are compressible. So whenever they are compressible, they can yield fallacies. The first apparatus regarding gas flow is the Benedict cross, as you can see, is made of a light bell. This bell has been settled on some amount of water to minimize the leak of the gases. This is attached by a pulley system with strings to a kymograph, where do we have a pencil drawing a graph, which it's sloping. It correlates the volume per time. You see, this apparatus is going to be used to measure the Fick principle of cardiac output, which we will discuss later on. The second instrument is the vitellograph. Vitellograph is some sort of concertina. Whenever the patient expires, one of the parts is being biffed, it's settled, and then this system is being activating, stimulating a motor system with a scraper which writes الخبطات. The moment the patient expires, this system reacts, also measuring the volume per time. These two instruments, as a matter of fact, measure limiting gas volume. The third one is the dry gas meter. As you can see, dry gas meter is being used in domestic homes, where we have 2 compartments, and we have a rod CC, as you can see. It attached to a lever. The lever is attached to gear and a pointer on the scale. This apparatus, the patient can whether expire or inspire, which is different from the other previous 2 instruments, where they depend upon the expiration of the patient. So this system moves the air between the 2 compartments, activating the lever system, where it can measure the volume of the expired or inspired gases. The fourth one is the Respirometer. We say the Benedict Gross Spirometer, but it's called Respirometer. It's made of a van, as you can see in the middle. This van is a very light metal attached to a gear system and a pointer on the scale. And then the patient expires. This air of expire circles, slits. Whenever it circles, it makes the van circulate, and then giving the tidal volume on the screen. And then once we finish, we press on the button, it returns back to 0. I'm afraid this instrument cannot give electrically recorded reading for analysis. This is the drawback of it, and it's difficult to be calibrated. You see, by time it can induce some fallacies. To avoid the dragging system of gears, as we know, any apparatus with gears makes a sort of dragging, so it affects the final results. We have, as we see, a van. This van is jeweled on a bar. You see, it's a special metal made of jewel, and it's attached to pedals. The pedals turn with slits, as you can see. Whenever the patient inspires or expires, this van is turned on, and we have a sort of light being detected by a detector. Whenever the van turns, it can estimate the amount of turning, and it calculate the tidal volume. This drawing on the upper right part of the screen. In the book, it's later on, but I wanted to utilize the space. We can see that the arrangement of the flow meters in the United States. We have the carbon dioxide, whether it's in the middle or on the last one. We have an auction is made in a special pathway, so that in case we have a breakdown in the middle of the flow meters, the auction will not be affected, as we can see from this B diagram. This system makes the constructions of the anesthetic apparatus to use what we call pneumatic mixing valve whenever we are using nitrous oxide or oxygen, to assure that we have a proper oxygen concentration, so that we will not have an anoxic mixture made of nitrous oxide. Of course, all the volume of gas we had mentioned above, most scientists always refer any volume of gas to the standard temperature of pressure. You see, the second point is liquid volume measurement. The simplest thing is to collect this liquid in a special jar. This jar is being graduated by liters, where we can measure the volume. The second thing is what we call the dilution techniques, where we inject labeled a small amount of labeled RBC. Suppose in the circulation, it will turn around the circulation, which is much affected by people with pheochromocytoma. So in people in such diseases, we must estimate the red blood volume and the plasma volume to attach both of them to get the final blood volume. So whenever this amount is being circulated and it's diluted, we can estimate the red blood volume from the equation which is shown in front of us, which shows the concentration of the label equals the dose over the red cell volume. See, so the red cell volume will be the dose over the concentration. Regarding plasma volume, we inject a small amount of radioactive labeled albumin, where it will circulation, dilute, and so forth, and we can estimate the blood, the plasma volume. At summation both, we can get the final blood volume. On the other hand, the blood volume, of course, can be estimated from the hematocrit, where whether we are using the plasma volume. If we use the plasma volume, we say 1 minus hematocrit. If we use the red blood cell volume, we say red blood cell volume over the hematocrit. Of course, to measure the extracellular fluid, we can use also radioactive labeled sodium. You see, the dilution also of sodium can estimate it. The third part in this lecture is what we call the gas flow measurement. And the commonest is the variable orifice flow meter. We call it variable orifice because it is made of a cylinder which is increasing from downwards upwards. You see, it's called rotameter. We can see from the left figure what we call the bobbin. The bobbin is made of aluminium, something like that. It's very light and it has slits. These slits make it turn, of course. And whenever the flow comes from downwards upwards, the bobbin is elevated and increasing the annual space around the bobbin. You see, whenever it goes upward, the annual space is the space between the bobbin and the wall of the cylinder is being increased, so that the upper part of this cylinder acts as an orifice, because the width is more than the length. So the upper part of this cylinder is affected by the law of turbulent flow, whereas the lower part is affected by the law of laminar flow. You see, so whenever the bobbin goes upwards and the resistance is being decreased as the annual space increase on both sides, of course the resistance will be decreased. You see, the pressure applied from upwards to downwards are equal, because the force of gravity will be balanced by the force of the bobbin ascend by this flow. You see, the problem of this bobbin, it may stick because it's whether it is in the upper limit of this flow meter or in the downwards. Also, the friction of the bobbin with the wood of the plastic container can create electrostatic electricity, which will affect the movement of it, so that most of the flow meters are applied with a special anti-static material to prevent the development of static electricity, or we use some strips. These strips are capable of taking off of this static electricity. We have on the right side what we call the needle valve. This is the part that is below the flow meter, where we have a knob. This knob is attached to a bar, a spiral. This spiral is attached to what we call gland and gland knot. This gland and gland knot are always present also in large cylinders to minimize the leak. You see, the speed of flow at this point is almost the speed of voice, so that the rules of flow is not governed because the speed is very high. Of course, we have a filter to prevent the dust. After that, we have the second variable orifice flow meter, which is the right peak flow meter. It measures the peak flow, which is around 400 to 500 liter per minute in a male. And whenever it reaches below 100, it means that the patient is suffering of problems. Of course, it's made of a van also. A van is attached to a gear system, as you can see. This van is being turned by the expiration of the patient and is balanced by a spiral downwards. You see, so whenever it moves, it's balanced by downwards, something that hinders its movement. It controls its movement. This is why its pressure, we call it a constant pressure. Meanwhile, when the van is being moved, the annual, the opening of the flow meter downwards is being increased to make the expiration escape. This gradual increase, as you can see from the figure, makes it a variable orifice constant pressure flow meter. We have after that, the third one is the pneumotachograph. Pneumotachograph is made of two compartments separated by a white gauze. This white gauze assures a laminar flow. The pressure drop is being electrically or electronically integrated to give the volume. Sometimes it is being heated by a heating element, so to prevent the condensation of water vapor, or to assure that the gas passing will not be affected by temperature changes, and of course the density will be affected, and of course the pressure drop will be defective. So we maintain the pressure by we maintain the temperature by a heating element. After that, we have what we call the Pitot Tube. This Pitot Tube is being used in airplanes, you see, to measure the velocity. As we know, any fluid passing has two types of energy. You have what we call the kinetic energy, which is responsible for the velocity, and we have a potential energy. P is responsible of pressure. So we have different types of energy, you see. So we have a tubing system where we want to measure the flow of what's going through it, and it's attached to a Pitot tube. The Pitot tubes are made of two tubes. These two tubes are attached to a differential pressure transducer. Of course, the tube facing the flow definitely will be exposed to more pressure than the other one, you see. So the flow going through it, its kinetic energy will affect the velocity. I want to tell you something, that the kinetic energy is proportional to the square of velocity. You see, so the final results that I'm trying to make the velocity correlated to the flow. You see, but you can say that the diameter of this tube is being changed, so I must maintain it by a special adapter to make always the velocity correlated to the flow. So this instrument, as I said before, is being used to measure the velocity of aeroplanes. The Pitot tubes, two tubes, the one facing is subjected to more pressure. The electronic mass flow meter, we can see, is made of a pass of flow, and we have two thermistors. It is thermistor, as we said before, it is a device to measure the temperature. You see, so the flow of the fluid is passing by. The depth of energy by the taking off of heat will give me a hint about the flow. Okay, you can say, okay, the flow temperature may be not 0 or 1, or I must figure it out from the first beginning by a second thermistor. So we have a thermistor that measures the temperature of the flow, and then we have another one which can estimate the drop of temperature by the flow. This is the method to measure the flow. After that, we have what we call the liquid flow measurement. Liquid flow measurement. Of course, the simple thing is to count the drops that are descent from a container per time, and we can multiply, getting the volume, know the density of this liquid, and we can estimate it. We have another instrument, as you can see, utilizing the light. We have a container. This container is filled almost third of it with liquid, and we have a dripping of the liquid. This dripping, of course, is affected by the gravity. You see, as we said before, the surface tension is a tension that makes the drop difficult to be detached. You see, it's trying to be attached to the surface. You see, but by time when this volume of the drop is being increased, it over this surface tension by the force of gravity, so it descends. So if we have a source of light, this light is being passed through the droplets and detected by a photo detector. Of course, we can estimate the number of drops passing per minute. On the other hand, if I want to control the dripper, I can attach a special bar. This bar is applied on the tubing system, where it increases the pressure to minimize the dripping rate. You see, it controls the dripping rate. Of course, we have, after that, we have we call it a gravitational. We are depending on the gravity for this drop to descend. On the other hand, we can use a syringe pump. It is motorized. You see, it is a motor that pushes instead of using the gravitational. Of course, we have also an infusion pump, which has a higher grade of administration, about 1 liter per hour. You see, so all this, the syringe pump and the infusion pump must be strictly administered into proper veins, so that we will not have a problem of extravasation. Of course, the flow meters, or as you say, the variable orifice flow meters, as we said before, we were using it for gases. We can use it in the artificial kidney and in the heart-lung machine also. You see, now we come to the last 2 points, which also measures the liquid flow, which depends upon the Fick principle. We have, as we see on the left one, this is the Benedict Gross, where it shows the slope of the volume per time. Whenever I use the chymograph, it draws a slope. So the patient inspired oxygen, again, is a rebreathing valve which absorbs carbon dioxide. It can estimate the amount of oxygen consumed in 1 minute. You see, suppose it is around 250 milliliters of oxygen per minute, and then we can from the slope. Of course, we are using, this is an invasive technique. We use the mixed venous blood to estimate the carbon dioxide content, and then we use the arterial line for the oxygen content. So we have 2 contents. You see, the difference of the 2 contents, suppose it is 20 in the arterial milliliter per deciliter, and in the venous 15, the difference is 5. So whenever I divide the amount of oxygen consumed in 1 minute over the 5, which is the difference, I can reach that the pulmonary blood flow is around 5 liters per minute. So if this is the principle of any measurement of any flow in any organ. If I know the concentration of the drug entering and the concentration of the drug leaving, and I know the rate of uptake, you see, I can get the flow of the blood through this organ. You see, so if I know the flow and I know the concentration of the drug entering and the drug leaving, I can estimate the rate of uptake, in other words. So this is what we call the Fick principle to measure the cardiac output depending upon the oxygen consumption. You see, we have what we call non-invasive measurement of carbon dioxide by differential Fick principle. This is another principle utilizing a patient on a ventilator. You see, this as we can see from the figure on the right, most downwards figure is an breathing system which we have a valve. This valve assures a rebreathing at different times every 3 minutes. You see, and then we have a flow sensor which measures the amount of flow of all the gases, and we have carbon dioxide concentration which senses the concentration. From these two parts, we can estimate the carbon dioxide concentration coming out, whether the patient is rebreathed or he is not rebreathing. In other words, this apparatus creates a non-rebreathing situation when I close the valve. So whenever I want to estimate the cardiac output, I have two equations. The first equation is the non-rebreathing. It is a normal. The carbon dioxide which can be estimated from the apparatus over the oxygen and the carbon dioxide difference between the arterial and the venous of the volume concentration of the carbon dioxide when the patient is non-breathing is created by this equation. On the other hand, if the patient is being rebreathed or rebreathing, I can create another equation. This equation, we call it rebreathing from, of course, these two sensors, as we can see on the right side. Why we create these two equations? Because it was found. If I rebreathe carbon dioxide, of course, the arterial carbon dioxide will increase. But on the other hand, the mixed venous blood will keep on not change for 50 seconds. So I'm utilizing this difference. You see, so whenever these two equations are being combined, we can finally get what we call the cardiac output will equal the volume of carbon dioxide rebreathing minus the volume of non-rebreathing over the arterial non-breathing minus the arterial rebreathing. You see, so every 3 minutes this valve is being closed, shut off. So we create a rebreathing. We create an equation of cardiac output. So we have two equations. These two equations are combined to make the final estimation of the cardiac output. The point is, it is not invasive because the arterial or venous cardiac, oxygen concentration can be evaluated from the end-tidal CO2. So it is non-invasive. I have a screen. I can, from the screen, estimate the cardiac output through the end-tidal CO2. Of course, we must put in our mind the shunt equation, which is around 5% of the total. This is the part of blood that does not undergo gas exchange. So we must put in our mind this amount to be subtracted. This can be measured by the oxygen saturation. You see, it's known that of course, if the shunt is being increased, the oxygen saturation be affected much. You see, and this the last equation, as we know, the volume of carbon dioxide, whether rebreathing or non-rebreathing, is the matter of an expiratory flow from this compartment times the fraction of carbon dioxide from the other compartment. You see, so this is a hint about the flow and volume measurement. We did it in a gas and we did it in volume. I hope that I succeeded and I hope that you understand all the points about it, and I'll be planning to make further lectures in the rest of the Bardworks book. والسلام عليكم ورحمة الله وبركاته.